We'll talk through this example I have here. Some examples. If you ever have x squared and you need to undo an x squared, you just take the square root. And the square root of x squared just results in x. It undoes that square. Same thing if I have like sine of x. If I want to undo the sine of x, I take the sine inverse of sine of x. Sine inverse and sine cancel out. We're just left with x. And kind of an often lamented and forgotten about guy is a to the x. If you ever want to get rid of a and just get x out, you have to take a log base a of a to the x, and that is your inverse, and you're left with x. So logarithms undo exponentials, trig inverses undo trig functions, square roots undo squares. Now, we have kind of a worked out explanation of how inverses work. So if you consider 2x plus 3, you start with your input. Whatever number you're plugging in, you start with that. And then order of operations says you're going to do your multiplication first. So your next step would be to multiply that by 2. Then your last step would be to add 3, and then you'd have 2x plus 3, right, Mark? All right. The inverse is going to undo your order of operations. So you're going to start with your input. And since your last step was adding 3, your first step of inverse would be subtracting 3. Then your last step would actually be dividing by 2. And I equate this to if you're putting on your socks and then your shoes. In order to reverse that order, you have to take off your shoes first and then take off your socks. So your inverse is actually going to do things in the opposite order and would use the inverse of that order. So if adding 3 is your last step, subtracting 3 would be your first step. If multiplying by 2 would be your second step, then your second step would be dividing by 2. That is what an inverse does, and that's what it is. We're going to start off with, how do you verify something is in fact an inverse? You can't just look at it and say it's inverse. You have to prove it is in fact an inverse. In order to prove that two functions are inverses, if you have two functions, f of x and g of x, if you take f of g of x and it results in just x, and you take g of f of x and that also results in x, then g and f are inverses of each other. I.e., if we have f of x is x squared, and your g of x is square root of x, no matter which order I do these in, x squared, take the square root, would equal x. And if I did square root of x squared, that would also equal x. So on this guy, if I was going to prove that this worked, the other order should work too. So if I had square root of x, and I squared that, that also equals x as well. So those are true inverses. There are equations that work one direction and don't work the other direction. So you have to check both ways, that f of g of x and g of f of x both equal x. So if we look at this example down here, and real quick, the domain of f must equal the range of g, and the range of f must equal the domain of g, and we'll talk about why that is in a second. All right, we're going to verify that h of x equals 2x plus 3 is the inverse of y minus 3 over 2. So in order to do that, we need to do it both directions. We have to do h of f of x, and we have to do f of h of x. So let's start with h of f of x. Now remember, all we're trying to do is we're doing h of whatever f of x is. So that is y minus 3 over 2. So if I plug that in for h, we are going to have 2 times that y minus 3 over 2 plus 3. Well, those 2's would cancel out. And I would just be left with x minus 3 plus 3. Our 3's would cancel out, and I'm just left with x. So that direction worked. Yeah?
How did it change from a y to an x? Or does it just not matter?
Oh, yeah. So we're going to end up with that y. Let's go ahead and, in fact, you know what? I agree with you. Just in the state of how I set it up, it doesn't really matter. As long as you get this out and you get this out. But let's, just for the sake of this problem, let's change that y to an x. Just so it makes more sense with how it's set up. Let's go ahead and change that to an x. I'll make them a little more sense with the definition that's above it. All right, so that direction makes sense. So let's go the other direction. The other direction would be f of h of x, which would mean we're doing f of whatever h of x is. That's 2x plus 3. So that means I'm plugging 2x plus 3 in for f of x's input. So then we are going to have 2x plus 3 minus 3 all over 2. Well, 2x plus 3 minus 3, our 3's would cancel out. We'd left with 2x over 2, which just equals x. That way works. I would make sure in my notes I put somewhere you need to check both directions. Because we've had problems like this before, and as I say, about 25% of you that are just like, I don't want to listen anymore, are going to get this one wrong. You're going to go one direction, go, nailed it, and then you're going to lose 2 out of 4 points because you didn't go the other direction. And that's just laziness with your notes and laziness with your studying. Because your studying should go through all your notes and look at any stars or anything you have on there. Okay. Next thing we're going to talk about are graph of inverses. Graphs of inverses. We are going to let f of x equal x squared as long as x is bigger than or equal to 0. And we're going to graph f inverse of x equals square root of x and verify graphically that they are in fact inverses of each other. So I'm telling you right now those are in fact inverses. I actually showed it up above. So those are two inverses. Let's see what the graphs look like when they are inverses. So let's go ahead and do f of x equals x squared for x is greater than or equal to 0. So let's pick some points. So we're going to do f of x first. So we're going to have our x, and we're going to have our f of x. Well, since it needs to be greater than 0, let's go ahead and choose 0. And let's choose 1, let's choose 2, and let's choose 4. All right, my function result would be then 0 squared is 0, 1 squared is 1, 2 squared is 4, and 4 squared would be 16. Now, I don't go out that far, so we're just going to plot those first 3 points. I'm going to do this graph in red. So we're going to plot, I don't like red. Let's do purple. So we're going to plot 0, 0. We're going to plot 1, 1. We're going to plot 2, 4. And that graph's going to look something like that. That is my x squared. All right, let's go ahead and graph the other guy. That would be our square root of x. We'll have an x, a square root of x, and we're going to go ahead and make that table. Now, I'm going to pick numbers I can actually take the square root of. It makes sense. It makes it a little easier than you don't need your calculator. So I'm going to pick the points 0. I'll pick the point 1. I'll pick the point 4. And let's pick the point 16. Sure, we could do 9.
I mean, 16 will go in the graph,
I'm going to do 16.
Okay.
I'm going to do 16 for a particular reason. You'll see why in just a second. But you could definitely do 9 and anything that is a perfect square. Yeah.
Just curious, does the x greater or equal to 0 also apply to the square root of x, or no?
Well, if you look at the square root of x, you can only plug in 0 to infinity. Yeah. Safa?
Can you just like flip the x and y?
Yes, that's what we're going to do. That's why I picked 16, and you'll see why in just a second. Because when I plug 0 in, I end up with 0. When I plug 1 in, I end up with 1. When I plug 4 in, I end up with 2. When I plug 16 in, I end up with 4. If you look at your function and your inverse, all that's happening is you are flipping your domains and ranges. That is all you're doing. So if you had a whole list of your functions, and I tell you just find the inverse of this, all you have to do is flip all those values, and you would now have all your points for your graph. So Safa's right. You just flip your domain and range. So I'd probably have some notes in there too. All we are is flipping our domains and ranges. And the graph of that, let's do this in green. A really disgusting green, but a green. We'd have 0, 0, a 1, 1. We would have a 4, 2, which would look something like this. Now, something interesting happens when you just flip your domains and ranges. And what happens graphically is it actually is going to flip it across the line y equals x. That will always happen when you graph your inverse. So on your homework, if it says check to see if those are inverses based upon the graph, you are just checking to see, did this reflect across that line? Or you can also check, did your x and y values switch? At 4, 2, do I have a 2, 4? That's an easy way to check it too. Just put some points on there and see if they are in fact flipping. So our two important things when graphing inverse functions on here is A, your domain and ranges just flip. Easy way to tackle inverses. The other way you could check to see if they're inverses is, hey, do they flip over this line y equals x? So there's actually a ton of important information on here. Safa. You do have to limit the x squared. Because, and we'll talk about that in a second, because there's a very strict limitation with these, but if I would come up here, that actually is no longer invertible, because that does not match this one. If it was positive, negative, this would not be a function. It has to result, we're talking about invertible functions. So the original function needs to be a function, and its inverse also needs to be a function, which we'll get to a horizontal line test on the next side, which will eliminate your concern about this, because you'd be like, oh, I can't even do this. It wouldn't be invertible then. So that's why I limit it to this one, so I can directly reflect it, not have to worry about doing the plus and minus, and not worry about not having a function at the end. Okay? It also goes back to this little statement here. The domain of f must equal the range of g. So if I don't limit my domain here to match my range of the other one, then I actually broke that one statement. All right, how to tell if a function is invertible, i.e., is the inverse of function. So how to tell if a function is even invertible? That was kind of what I was talking about with it wouldn't result in a function. It needs to result in a function to actually be invertible. So a function's inverse is also a function only if the original function is 1-to-1. A 1-to-1 function is a function such that no y value corresponds to more than one x value, the opposite of a function. A function was, the definition of a function is one letter can only go to one mailbox. In order for it to be invertible, we have to stick with one mailbox can only have one letter going into it also. So that is your definition of invertible. It goes the opposite direction. Once again, a function is no x value can go to two y values. To check to see if something's invertible, you're going to make sure no y value goes to two x values. All right, and we'll see that down below. Down below, our example says, determine if the following are functions, and then tell if they are invertible. So we're going to go in both directions. So we're going to check to see if they're functions first. So we'll do a domain. We have 3 elements of our domain. That would be -2. That would be a 4. and that would be a 2. Then our range would be 3, 5, and 6. Well, 2 maps to 3, 4 maps to 5, 2 maps to 6. That is definitely a function. Reminder, the only time it's not a function is if, say, -2 goes to 2 locations. Then it's not a function. These are your envelopes. These are your thing. So mailboxes. I don't know why I couldn't think of mailbox for a second. All right, so that means they are functions. When you're checking to see if something's invertible, you're going to draw your arrows the opposite direction. So we're going to still stick with our domain being -2, 4, and 2. We're still going to stick to our range being 3, 5, and 6. And now we're going to go backwards. We're going to say, okay, this element in the range maps to -2. 5, which is an element in the range, maps to 4. 6 maps to 2. Because there are no arrows that go to 2 different things, this would also be invertible. So what it means to be invertible. The actual function works, it's a function, and its inverse would also be a function. Both directions would be a function. On our next one, my guess is it probably won't be invertible, because it'd be pretty boring if I just had both that worked. So our domain is 3, 5, 7, 9. Our range is 1, 2, and 4. All right, 3 maps to 1, 5 maps to 2, 7 maps to 4, 9 maps to 4 as well. Is that a function?
No. Yes.
Yes, it is a function. Letter 7 and letter 9 can both go to one mailbox. It is still a function. Remember, the only time it's not a function is if I have to branch 2 arrows from the same number. So this is a function. Now we're going to check to see if it's invertible. So we have our domain elements, which are 3, 5, 7, and 9. Then we have 1, 2, and 4, our elements of our range. Well, if I go backwards, that 1 would map to the domain of 3, 2 would map to 5, 4 would map to 7, and 9. That would not be invertible. Yeah, Mary.
So it's the one on the right that can never have 2 things like have 2 different numbers.
Are we talking about function or invertible? So this one is a function,
Right.
so it's fine.
Right.
It's just not, its inverse wouldn't be a function.
Okay.
Because Mary, remember when we actually do our inverse, our domains and ranges flip. So if I was looking at my inverse, this would actually become my domain, and this would be the range. So my inverse would not be a function. Yep, so that's what we're actually checking for. If I switch my domain and range, would it still be a function? And in this case, it would not be a function. So it's not invertible. It's still a function, but its inverse would not be a function, is what we're saying. The inverse would not be a function. Jacob.
What if we had like 3 numbers for the domain and then 4 for the range?
Mm-hmm.
So that the function, it would be a function, but it can be invertible. Is that possible?
Can you give me a quick example? So you're saying
1, 2, 3, 4 on the domain side.
Okay.
Then 4, 5, 6. Or actually, erase the 4 on the left side.
Okay.
And then add like a 7 on the other side.
My right side or left side?
Right.
So 7 down there?
Yeah.
Okay. So that's my domain and that's my range. What do you want 1 mapping to?
4,
4. 2 goes to?
5,
3 goes to?
6, and 7.
6 and 7. So that is not a function, but its inverse would be a function. Yep. So Jacob's correct. This would not be a function, but its inverse would be a function. What this most likely would be is maybe you have something that looks like this as your function. Maybe it was that plus or minus thing. So that is not a function. But if I took the inverse of this and flipped it across that y equals x, you'd end up with that red line, which would be an x squared. So this would be a case where it's not a function, but the inverse would be a function. Yeah. All right, so that is our checking whether it's invertible or not. The next thing we're going to talk about is how can I tell if it's invertible or not based upon a graph. So we can check to see if something's a function by doing something called a vertical line test. In fact, let's do the vertical line test on both of these. Both of these would pass the vertical line test because if I drew a straight line, if I just drew a straight, let's change the color of that, make it stand out a bit. So if I drew a vertical line anywhere, it only hit at one point, which means it is in fact a function. The next one would also pass the vertical line test because no matter where you draw a vertical line, we would say it only hits in one place. Remember, if it hits in more than one place, it fails the vertical line test. In this case, it just hits in one place, so that's a function. Also, I do want to remind you, if it hits in no places, it's also still a function. It's just 2 or more places. So 0 places works. So in fact, if we just drew a little, let me just rehash what I'm saying there. If we just drew, say my graph is just that. That's a function. It's hitting nowhere, 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 1, 1, 1, nowhere, nowhere, nowhere. That is still a function. All right, so both of these are functions. Now to check if it's invertible, in other words, is its inverse going to be a function, you're going to do something called the horizontal line test. You're going to do the horizontal line test. So that means you're just going to take a straight line, string it across, and see if it hits in 2 or more places. In this case, it does. It hits in 1, 2 places, so that means it's not invertible. And in fact, you can kind of think about this. If I flip this across that y equals x line, this would be sideways and it would no longer be a function. Right now it's a function, but the inverse, which would flip across that y equals x line, would not be a function. In this next case, if I did a vertical line test or a horizontal line test, no matter where I put that horizontal line, it's only going to hit once, so it is in fact invertible. Yes?
What if you put the horizontal line on the x-axis?
That's fine.
But like,
It's only hitting once,
where?
right at 0, 0. This point right here is slightly below. This point right there is slightly above. This is just an x cubed graph.
Okay.
X cubed only hits at 0, 0. All right, so that one's invertible, and it's a function. The other one is a function, and it's not invertible. All right. Now finding inverses. So we know how to check to see if something's inverse. We know how to check to see if something even has an invertible function. Now we're just going to go ahead and study this stuff, guys. I put this on the test. I just put 3 graphs and said, are they functions and are they invertible? There was 3 graphs. I'm 99% sure I'm going to do it again. And you just have to say, is it a function and is it invertible? So if you know your vertical and horizontal line test, you start your notes, that's going to be 3 easy problems. If you don't, then you're going to be that person that loses probably 8 points just because you didn't look at your notes. All right. In order to find an inverse, all you have to do is swap your x and y values and then solve for y. That's all you need to do. So in this case, it says find the inverse of f of x equals 5 minus 3x over 2. So what we really have is y equals 5 minus 3 of x over 2. To find the inverse, you're just going to flip your y and your x values and solve.
How do you do that?
Just like this. See that y value? Boom.
Oh.
See that x value?
Yeah.
Boom. You literally take your x and y's and you change their locations.
So,
No matter how many x's you have or no matter how many y's, you swap them all out. And now you need to solve for y. So to solve for y, the first thing I would do is I'd multiply both sides by 2. That would give us 2x equals 5 minus 3y. Let's subtract 5 from both sides. We would have 2x minus 5 equals negative 3y. And finally, I would divide everything by a negative 3. We would end up with negative. Let's put that negative on the bottom. Let's keep it with that 3. Equals y. And we can just stop there. That is our inverse. That's all you need to do. Swap your x and y and solve for y. All right, I think I have 2 more examples here. It says find the inverse of h of x equals the cube root of x plus 1. Once again, I would write it with a y in place of the h of x. We'd have y equals cube root of x plus 1. Then I would switch my x and y values. So I'd have x equals the cube root of y plus 1. Then I would cube both sides to end up with x cubed equals y plus 1. And finally, I would subtract 1, and we'd have x cubed minus 1 equals y. All right, the last one says find the inverse. Oh, no.
Why do you do that?
Yeah.
Did you just say y equals and then the rest of it?
No, we'll stick with mx equals. That's fine. We can change it to an inverse in just a second, but I would just flip the x and y values. There's nothing to solve for this time. We just flip the x and y values. And what I would do is I'd add an inverse up here. And inverse of x equals, and we'll change these to 2 comma 3, 0, 1, and 6, 5. In fact, we should probably go back and change these notations. We should probably change this notation to, do we have an F or do we have a G in that? We had an H. We should probably change this to H inverse to let the reader know that that is an inverse. It's not your regular y. It actually is your H inverse of x equals x cubed minus 1. So that's probably a much better way to put it. And we could do the same thing down here. Rewrite that one as F inverse of x equals 2x minus 5 over negative 3. Just to let the reader know that that is your inverse of your original function. That way they're not deciding what that y equals. Was that an original y? Is that a new y? So we should just really change those into the inverse of the original function that was stated there. Bless you. Mark.
Can I go to the bathroom?
Sure. All right. Any questions on what we covered today? Once again, this assignment isn't due until next Wednesday. We will have a review, and since Emma asked, I will post the review online. Hey guys, real quick on the Google Classroom, if you're printing stuff out, everyone pay attention really quick. I did put a note on there. I don't know how many people actually checked the stream of it. But for right now, Google had a big update on it. When you click on a file, you can normally just hit print or Control P and it would print it out. That no longer works. There's like a grayed out box. All you need to do is use a little computer intuition and just right-click on the file rather than left-clicking on it. And you right-click it, and you can usually open something in a new tab, right, when you click a link. So rather than clicking the actual file, left-clicking, you're just going to right-click and then go open in a new tab. And then you can print and download and do whatever you want with it.
Why did Google do that?
I don't know. Alternatively, when you click on it, so if you're one of those people that usually clicks on it, and you can usually just hit that print icon, right next to it has 3 dots, which are more options. And in those 3 dots, they have like open in a new tab also. You can't just download it and print it too, but some people don't know how to get to the download portion. You have to do one of those 2 options to actually download it.
That's like
It takes a little computer knowledge. All right, since we're done with this, what questions do we have from the homework? Nora.
number 61.
Yeah. 61 is let f of x equal absolute value of x. It says g of x equals x minus 7, and it says h of x equals x squared. You have to come up with a composite of functions such that your new function f of x equals x squared minus 7. So there's no absolute value in it, right?
Yeah.
So I really only care about g of x equaling x minus 7, because that matches that minus 7. And we also are going to focus on h of x equals x squared. And what I'm thinking of is if I just took this x squared and put it in place of that x, I would have x squared minus 7, right? So what I'm actually doing is I'm taking h of x and inserting it here. So I'm taking h of x and plugging it in place of that. So we are actually looking for our g of x is kind of our parent function. So I have g of h of x, which would also be Does that all make sense, though? Okay, good. Safa. 59. 59 says h of g, f of g. Oof, indeed. All right, so we have three functions. We got f of x equaling x minus 2. We're supposed to come up with a domain also, right? Yeah, so we're supposed to also come up with the domain. All right, so let's go ahead and look at this. So we need to end up doing, at the end of the day, I need to do h of f of g of x. Let's just focus on this part right here, the f of g of x. Well, f of g of x, bless you,
Thank you.
would be f of whatever g of x is. So f of and g of x was square root of x. So if I plug square root of x in place of f, we would have square root of x minus 2. Then to finish this off, we're going to do h of square root of x minus 2. Our h of x is 1 over x, so it would just be 1 over square root of x minus 2. So that's my function. Now I have to come up with the domain of this. Well, the first thing I'm going to recognize is 4 is not going to work. Can't be 4. So 4 does not work. So 4 messes this up. Then I'll look at the domain of all of the other functions. So if you look at h of x, there's only one value h of x can't be, and that is 0, because it's 1 over x. It's all values except for 0. Then we look at g of x. G of x is square root of x. That is any number that's positive. So that's 0 to infinity. And finally, f of x is negative infinity to infinity. So the real constraining one is the one that goes from 0 to infinity. So that's our first overlap, but it can't be 0 because of the 1 over x. So we get rid of the 0, so now we just have 0 to infinity, parentheses. And it also can't be 4. So it's 0 to infinity with parentheses, except 4. So it should be, you can either say just like that, or you can go 0 to 4, union 4 to infinity. Other questions? Jacob.
70.
70 says, determine whether the following is a true statement. So it says f of x equals x plus 1 and g of x equals x. So we're supposed to do f of g of x and g of f of x. So we're inserting f of x into g of x, and then we need to insert g of x into f of x. So that would be our f of g of x would equal f of, and g of x is just 6x. And when I insert that 6 of x in for the x of f of x, we would have 6x plus 1. Then when I do g of f of x, well, f of x is x plus 1, so I'm really doing g of x plus 1. G of x is 6x, so that'd be 6 times x plus 1. Make sure we distribute we'd have 6x plus 6. They said those two things are equal. I disagree. Those are not equal. The big thing is, what this problem is getting at is make sure you keep things in parentheses. Because at first, if you didn't have parentheses here, it would look the exact same. It would say 6x plus 1. But the parentheses are what make and break this problem. Other questions? Good. All right. When's this homework due?